Okay, welcome. This is Mr. Dahlstrom helping out doing some of the AP Physics problems that we worked on after school today. So there's 4 here. If you already solved them, great. This is just another way of explaining. This is some of the stuff we went over before. We're first going to look at, number 72. 72 is an example problem where you have a bullet that's being fired into a block. The bullet then gets stuck in the block, and the block and the bullet combination go and reach some height. So what we're trying to figure out here, what is asked of us in the book is, so we'll go back to the page here, is they're asking for us to describe how you would find the initial velocity of the bullet. So describe how we would figure out what that is, and then find an expression for the initial velocity of that. So this one uses 2 conservation laws. So the law of conservation of energy will allow us to figure out what the velocity of the combined masses is here, and then if we know what the velocity of the combined masses are, we can work backwards to figure out what's the velocity of the bullet itself. So the conservation of energy, so instead of thinking of the bullet, let's work backwards. The amount when the block bullet combination, which is m plus big M, small m plus big M, is at its maximum height here, we have a gravitational potential energy equaling our kinetic energy. So the kinetic energy of the combined masses is converted completely into the gravitational potential energy of that. So if we take 1/2 times the combined masses times the velocity squared and have that equal the mass, the combined mass is GH, we can basically use that to solve for what this velocity would be here. So let's go ahead and actually solve for this velocity here by rearranging some stuff. So if we take this stuff over to the other side, we get v squared equals 2, there's where that goes there, times the quantity m plus big M, GH, divided by the quantity m plus big M here. And we can see what cancels out is that cancels with that. And we end up with for this v is the square root of 2gh. Now realizing that that velocity of this combined mass system is the velocity of this right here. So this velocity is that velocity right there. Because this is, so we have the bullet that's being shot into the block. So this is the momentum of the bullet before it hits the block. This is the momentum of the block before it gets hit with the bullet. And here is the combined, this is the momentum of the system afterward with 2 masses together. So we need to rearrange this to solve for this. Now it seems fairly complicated, but if we realize something's actually 0 here, this block up here is not moving, so the velocity of big M here is 0, which makes this velocity right there go to 0. So I have basically M times VIM, which is just the velocity, the initial velocity of the bullet, equals m plus big M times the square root of 2gh. And so to solve for this velocity, so that's the velocity of the bullet, the velocity of the small m, we get quantity m plus big M times the square root of 2gh, all divided by little m. And that's the velocity. It doesn't look nice, but that is the velocity from that. So once again, we use the idea of conservation of energy that we could, if we knew what the height was here, we could figure out the velocity of the combined masses. Once we know the velocity of the combined masses, which is really just 2gh, we plug it down into here and use the conservation momentum, that the momentum of the bullet and the momentum of the block before has to equal the combined momentum of them together in this inelastic collision. Rearrange it, and we find this initial velocity here. So there you go. That's number 72. So it's nice when we have these understanding, hey, we can't always use conservation of energy when we're talking about momentum, but if we realize there are 2 different steps, that the block rising up to the highest point is a conservation of energy or energy transformation problem, while the bullet hitting the block causing that to go up is a conservation of momentum problem. The next one we're going to look at is number 76, and this is one where it is saying, why is the following situation impossible? So I've already solved a little bit of this. Let's kind of define some things here. So we have an astronaut that unfortunately pushed off of the spaceship and is now traveling 20 meters per second away. I try to kind of help you figure out what's kind of going on here. And so you have what I'm calling ME, which is the mass of the thrown equipment. So what he's trying to do is that it tells us that when he's floating away, that he throws some equipment away at 5 meters per second, and because he's trying to get back. We talked about that in the past where, hey, how can we get back? So just a few things. So the mass of the thrown equipment is little me, and the mass of just the astronaut by itself is ma. This will make sense a little bit later in showing why this doesn't make sense. So they tell us in the problem that the combined mass of the astronaut and all the equipment is 150 kilograms. So we need to figure out, so once again, at some other point he throws, so I need to draw over here, at some other point, the astronaut, while the astronaut is moving 20 meters per second this way, actually throws some amount of equipment that way at 5 meters per second, and we need to figure out what is the mass of that equipment that was thrown away. So here, we'll set up our equation here, and we're trying to say that the momentum, we're just trying to figure out what is the mass needed just to stop him. So he's moving at 20 meters per second, so this mass thrown here is just the amount needed to stop him, because this is the amount of momentum he has before the throw. And so if we want to stop him, meaning to cancel those out, meaning positive momentum, negative momentum to cancel out, we have 150 kilograms, which is the combined mass of the equipment and the astronaut and the 20 meters per second, which he's already moving. And then afterward, you're saying, why don't we have big M there? Well, we're just figuring out how much mass of the equipment we would need just to get this to work. So for this side here to equal this side, this is the equipment being thrown at 5 meters per second, we can calculate that the mass of the equipment is 120 kilograms. Now we have to remember that the mass of the astronaut itself, so the mass of the astronaut and the equipment is 150 kilograms. If the equipment thrown is 120 kilograms, that means that the astronaut's mass is 30 kilograms, which means the astronaut is 66 pounds. It says that it's unreasonable. I'm not saying that the student I was working with, we were saying, well, it's not technically impossible for this to happen. And the joke was maybe that it was a monkey. If a monkey was 66 pounds, or big monkey, threw away 120 kilograms of equipment at 5 meters per second, that would allow the monkey just to stop. So the monkey would actually have to throw more than 120 kilograms. This 120 kilograms just to get him to stop moving relative to the spaceship. Any more mass thrown this way, any more mass thrown would actually get him moving in the other direction. So they prove why this is impossible. I guess it's saying that the amount of mass needed to be thrown is 120 kilograms, leaving at least 120 kilograms, leaving the mass of the astronaut being 30 kilograms, 66 pounds. So unless you have a child astronaut or a monkey or something else, it's not possible in this case here. So that's number 76. So once again, you see why separated. I wanted to kind of split it up in terms of the mass of the equipment, mass of the astronaut, the total mass of both of those with the total momentum they have before. We would say how much momentum do we need basically to stop that, and it's 120 kilograms, and that's why it's unreasonable. It's not. I wouldn't say it's impossible. It's possible, just highly improbable. So that's why, because the mass is so small. The next one we are looking at is number 80. Number 80. So number 80 is a problem where if you first look at it, you're like, whoa, what's going on here? Do we need to use force? Is there calculus involved? So number 80, we have a mass. It's called M1 slope up here. Excuse me. And let me write down some of the information. It gives us the mass of this is 0.500. Hold on here. Check my stuff. Yep. And it tells us the mass 2 is basically some ramp. It's on some frictionless surface, so that when this mass slides down the ramp, this is also frictionless, but it slides down the ramp, it pushes this to the left and this goes to the right. So it starts off at rest here. When it slides down, eventually when it slides down, it says that this is now traveling at 4 meters per second, and we're trying to figure out some information. We're trying to figure out how fast this goes in this direction. So let me write a couple more things out here. M2 is listed as 3 kilograms. We're told that the velocity of the block here is 4 meters per second. So if you look at this, first we were looking at something, oh, do we need to know the force? But if you think about it, we have two objects that are together in the beginning. Some action takes place, and we have two objects that are now separated. In pre-AP physics, we called this a recoil or an explosion type problem. This is the way you solve this is exactly the same way that you solve how fast is the recoil of a rifle when a bullet is shot. Basically, this would be the rifle, this would be the bullet. You know how fast the bullet comes out, and you can figure out the velocity of the rifle on the other end. Excuse me, I just have a little bit of allergies here. So this is our recoil explosion one, where you basically have a combined masses before with their initial velocity. You have and then the momentums afterward. Now, one thing that is nice in this equation here is that the initial velocity of this system here is 0, so that is all 0. Now we just plug in what we know. So M1 is 0.5. The final velocity of that is 4. Mass 2 is 3 kilograms, and V2F, we would expect this to be negative because it's moving to the left, and it is. When you solve for V2F or VF or whatever it happens to be here, 0.5 times 4, subtract that, so negative 2 divided by 3, or negative 2/3 meters per second. So there we go. That's how fast that thing's going to go back. What they next want to know, they want to know how high, what is this height here in order for this to happen. So whenever I'm thinking about height and dimensions height, I'm thinking, okay, this has to be a conservation of energy. Here's a conservation of momentum, here's a conservation of energy, and it is an energy transformation. So we have to think about all the energies that we have going on when we're looking at this block, because the block is basically what is introducing, I guess, energy into this. So the block at the top has some gravitational potential energy. All of that is being converted not just to the kinetic energy of the block at the end, but also the kinetic energy introduced into the slide or whatever, the ramp here, pushing it to the left. So we have this equation here. This is the potential energy. So we have M1 times G times H. Here's the kinetic energy of this, and because kinetic energy is a scalar, it doesn't matter that you have a negative 2/3 here. When you square it, it's going to be a positive number there. And then we have the kinetic energy of that. So this potential energy stored in the block is converted completely into the kinetic energy of the block and the ramp that we have here. And on another paper, I already solved for this here. So instead of using PG, so 0.5 of the block times 9.8 times H equals 1/2 the mass of the block. There's the velocity. That's the velocity that they told us how fast it was moving there, and squared it. Plus 1/2, so once again, this is the block, and this is the ramp. So 1/2 times the mass of the ramp times the velocity. We can put negative there, it's not going to matter when we cancel that out. Solve for that, 4.9 H equals 4 plus 0.66 repeating, and when we solve for H, we get 0.95 meters. So this interesting problem, similar to the one in the last one, where one part of the problem we had to figure out how to solve it using conservation of momentum, realizing that the situation is basically akin to a rifle and a bullet before, and then afterward we have the rifle here that's moving to the left, and we have the bullet that's moving to the right, and we can use that to figure out the velocity. So there's number 80. And the last one we're going to look at here is, find my paper, is number 81. Find this. Number 81 is a review problem. And I really like the way the review problems work in the AP book, because when you first, in like the first chapters of kinematics, you're doing a review, you're like, oh, I'm not really good at projectile motion. But then you do forces, and they have you do projectile motion to get better at. Then you have you do energy and projectile motion to get better at. And then finally, momentum, you're having to use projectile motion. So you're almost like, this is really easy. So this is the setup here. We have another bullet in a block. The bullet is fired into the block, sticks into the block. The combined masses going horizontally off of this, so this is a horizontal launch problem, land 2 meters away from where it took off here. They tell us that the height here is 1 meter. And so what we're trying to figure out is we're trying to figure out how fast, let me just double check here. I think we're trying to figure out how fast is the bullet traveling. Yeah, so it says determine the initial speed of the bullet. So we're trying to figure out how fast is that bullet right there moving. And so this is a backwards problem. We can't figure out how fast that's moving until we know how fast the combined masses are moving. We can't know how fast the combined masses are moving unless we figure out how fast, how fast it has to go for it to travel 2 meters. So first, we're going to find the initial velocity of the combined projectile here. So once that hits, this flies off here. Basically, in our kinematic equations here, we're trying to figure out Vx. So some velocity is going to cause it to fall 1 meter and travel 2 meters here. So I set this up here, and our velocity in the x direction is what we were trying to figure out. Our delta x here is our 2 meters, and we don't know the time. Okay, so not enough in that direction. We don't cry ourselves to sleep, not yet. The initial velocity in the y direction is 0. The reason being is that it is cosine of 90 degrees, also because it's a horizontal launch. Delta y is negative 1 meters because it's going down. T we don't know. G is negative 9.8. And we would necessarily might need the final velocity, but in this case we do not need it. It's very helpful that the initial velocity in the y direction is 0. So we need to find some equation that has delta y, VIY, G, and T in it that allow us to solve for that T. And if we use what I call the quote-unquote third equation for my class, delta y is equal to VIY T plus 1/2 GT squared. Now, originally we would have to use the quadratic here, but because the initial velocity in the y direction is 0, that goes there. Delta y equals 1/2 GT squared. There's your T. So let's plug it in. Negative 1 equals 1/2 times negative 9.8 times T squared. And when you solve for the T, go ahead and use, I think I used 9.81 actually last time. So 8, square root that answer. And we get about 0.45 seconds. Okay. So check the numbers, yep. And so once we know what that time is right there in the y direction, the time it takes to drop is the same exact time that it takes to travel sideways. We now know that this is also 0.45. And we can use our kinematic, since there's no acceleration in the x direction, Vx equals delta x over t. Delta x is 2 meters. Time is 0.45 seconds. So Vx comes out to be approximately 4.44 meters per second. All of that review there, just to figure out how fast these combined masses are moving. Now, how does that help us? The reason it helps us here is that this is an inelastic collision. Here's the momentum of the bullet before. Here's the momentum of the block before. Here's the momentum of the combined masses. This velocity is how fast the combined masses are moving once they collide together. So we know V. So let's go and figure out what we know in this. We know the mass of the bullet. We know the mass of the block. And we know the initial velocity of that. It helps us here because it's not moving. So once again, that's 0. You see there. We know the mass of that. We know the mass of that. And we now know that. And the only thing that we do not know is the initial velocity. So let's go ahead and plug this in. Mass of the bullet, 0.008. Initial velocity of the bullet. That goes to 0, so I'm not even going to write that because it's, I guess, 0.250. I guess we'll put it there. Times 0. That's why that goes to 0. Equals 0.008 mass of the bullet plus the mass of the block. And now we know what V is, and the combined masses are moving 4.44. And when you solve for that, all things said and done, we get an initial velocity that is about 143 meters per second. And you're like, that's fast, but then you realize that that is also a bullet, so that's not out of context. That's about, I don't know, let's say the speed of sound is 343 meters per second, so it's certainly not faster than the speed of sound. So it's relatively simple there. So once again, we had to know, in order to know the velocity of the bullet. We had to know the velocity of the combined masses. In order to find that out, we had to figure out what velocity would allow us to fall 1 meter and travel 2 meters sideways. We figured out the velocity, therefore we could work back and find the initial velocity for the bullet. That wraps up today's little lesson here. I just felt like I had some time and I kind of understood this. So good luck on your test on Friday. I'll try to load this here, and thanks for watching. Subscribe.